Hello everybody, in this lecture we will be solving 1970 IMO problem number 4. This will be a second proof for this problem. We would like to find all positive integers n such that the set of 6 consecutive integers starting from that integer n can be partitioned into 2 subsets so that the product of the numbers in each subset is equal. Okay, I would like to start with a claim, and my claim is simple. I claim that no such partition exists. And to prove that, I will assume to the contrary, that such a partition exists, that such a partition exists, and we will find a contradiction. Exists. Well, there are two cases. Case 1, exactly one of the 6 consecutive integers will be divisible by one of the 6 consecutive integers is divisible by 7, but then that's impossible, right? Because that integer which is divisible by 7 will fall into the one of the sets, and let's say that the product of that first set is equal to A and the product of the second set is equal to B. So if 7 falls into this set, so the product A will be divisible by 7 versus the second set will definitely not be divisible by 7. As a result, there is no way that those two products of these sets will be equal to each other basically. So therefore, we are only left with one case, case 2. None of the 6 consecutive numbers are divisible by 7. What it means is that in mod 7, they will have a remainder, they will leave a remainder of 1, 2, all the way to 6, up to 6 as remainders, right? Remainders. So what I will do next is let's keep the same notation. Let's assume that the product of the elements in one set is equal to A and the products of the elements in the other set is equal to B. So what I will do is I will multiply all these numbers. So n times n plus 1 up to n plus 5. Well, this is congruent to, we have established that it's equal to 1 plus 2, 1 times 2 times 3 times 4 times 5 times 6, because we established that none of them is divisible by 7. And by Wilson's theorem, by the way, this is congruent to AB, right? So this is, let's just write it AB. So A times B is equal to this. And by Wilson's theorem, we know that this is simply equal to minus 1 in mod 7, right? Remember Wilson's theorem saying p minus 1 factorial is equal to minus 1 in mod p, where p is prime. But for a and b being equal, it would mean that we should have a square, right? So minus 1 must be a square in mod 7, which is not the case. Minus 1 is not a square in mod 7, and this is the desired contradiction, suggesting no such partitioning exists, and we are done. So hope to see you guys in our next video.